So let's go ahead and look at another example of proving logical equivalence. And here I've already written it out. We need to prove that the following statement is always true. And the statement is given to us in English. It's a little bit difficult to parse, because let's read it. It is not hot, provided that both it is raining and it is not raining whenever it is hot right here. Well, that's hard enough to parse as is, not to mention trying to figure out if it's always true or not. So I'm definitely going to have to take my first step right here and translate this English statement right here into a logical expression. And only then can I apply the rest of my steps right here to try to prove that this statement right here is always true, or that it's a tautology right here. So the very first step in my proof is I'm going to have to translate this here into a logical expression. So if we look at this sentence right here, it is not hot, provided that both it is raining and it is not raining whenever it is hot. I notice that it's only really talking about hot and raining and hot. So I basically have two variables right here. And I'm going to let P be the expression, it is hot. And I let Q be it is raining. So I can't immediately jump to some logical expression for this English sentence right here. So I'm going to take it step by step for this translation step right here. So let's start at the very beginning. It is not hot. Okay, it is not hot. So that's going to be a not P. Provided that, well, I'm just going to leave that for now. Provided that both, okay, well, provided that both, so this both is a synonym for and I know it's going to apply to the rest of this piece right here. So it's going to apply to some compound proposition right here. So let's see what it is. It is raining. It is raining. Well, raining was Q, so that was a Q. We have a both, so that was an and then we have this piece right here. It is not raining whenever it is hot. Okay? It is not raining. So that would be not Q. And then I'm going to leave the whenever. It is hot. Well, it is hot was P right here. Fantastic. So I'm one step closer to getting a logical expression for this sentence right here. But I need to recall what this provided that and whenever are. So these are keywords for implication. And so we have to recall that of the many different ways that we could pronounce this implication right here, P implies Q, two of them were Q whenever P and Q provided that P. So whenever we see our keywords provided that or whenever, we know that the hypothesis shows up to the right of those keywords, and we see that the conclusion right here shows up to the left of those keywords over here. So I have one of those keywords right here, so I know that this is an implication where that part is a hypothesis and that part is the conclusion over here. So I could rewrite this. This is the hypothesis. And this is the conclusion. Great. One step closer. So here I have a whenever. Again, what's on the right-hand side is the hypothesis of my implication, and what's on the left-hand side is the conclusion of my implication. So here, this is going to become Q and. Now here, that's my hypothesis. And this not Q is my conclusion. And that whole thing implies not P. Whew, great, okay. So I've successfully been able to translate this English sentence over here into a logical expression. So the next thing that I need to do is to prove that this statement right here is always true. So what this really wants me to show is that this expression is logically equivalent to true. And so what we're going to try to do is apply those steps right here to do that. So now let's go ahead and try to apply this general approach right here to show that this statement right here, this translation of that English statement, is always true. So I'm going to rewrite this expression right up over here. So we have this expression. And what we want to show is that this thing is always true. Okay, fantastic. So once again, I don't see any immediate identities that I can apply to be able to simplify this thing. So I am going to reduce it to ands, ors, and nots. And in particular, right here, I'm going to take this implication and I am going to rewrite it in terms of its definition right here. So I know that this thing is going to be logically equivalent to, so I take my hypothesis and I negate it. So I negate my hypothesis. Or, and then I leave my conclusion right here. So I did this by definition. Great, fantastic. So now, let's see here. I could apply De Morgan's law to try to distribute this not right here into that expression. So then this thing would become, I know De Morgan's law puts the nots in front and it flips this and to an or, and then I take a not of this expression right here. So here I used De Morgan's law. And I would like to be able to use De Morgan's law again right here, but this is an implication. So again, I'm going to have to, by definition, rewrite this as its definition. It's going to become and here, once again, I used the definition of implication. Great, so now I can apply De Morgan's law right here and distribute this not into this expression right here. Flips the or to an and. And here I see some double negation right here. So after I had applied De Morgan's law, I can go ahead and get rid of this double implication or the double negation right here. And I see that I could distribute, because I have an or and an and right here, I could distribute this not Q over into this expression right here. So let's go ahead and do that. I'm going to distribute this not Q right here into that expression. And so I'm going to get not Q or P and not Q or Q. Fantastic. So here I use my double negation, and then here I used my distributive property right there. And I notice, hey, look at this. I can use one of my known identities. I have a not Q or Q. So I know that this thing right here is always true. So since this thing is always true, I could rewrite it as that. And so this is another one of my known identities right here that I have applied. And by the law of domination, I know that this expression right here is only going to depend on the truth value of this left-hand side over here. So rewriting it, I get this expression. So here I have used the law of domination. And here I used one of my known identities. We're almost towards the end right here. Once again, I see that this thing only involves ors right here. So since it only involves ors, I know that I can use one of my manipulation rules, and I can use associativity to regroup these parentheses and get this. So here I used my associative identity right here. And fantastic! I can apply one of my known identities, P or not P. I know that that statement right there is always true. So this thing is going to be logical equivalent to not Q or true. Haha! Fantastic! I'm finished, right? Because I know that this or right here is going to be true whenever either the left-hand side or the right-hand side is true. And indeed, this right-hand side right here is true. So I know that this thing is, in fact, always true. So after applying all these steps right here in succession, I have been able to show that this logical expression right here is logically equivalent to true all the time. So therefore, I can claim, yes, this English statement right here is true. And once again, this shows you the power of being able to use these known identities to take some complicated English sentence right here, reduce it down, and prove without a shadow of a doubt that it is always true.